Go on. So a few things we highlighted. We talked about the chip itself, and we mentioned a bit about the registry and the port. So for the port, we mentioned that the 18MegaThread2AP has 3 ports that we have access to, which is port B, port C, and port D. On the Arduino Uno board, port D0 obviously is connected from digital pin 0 all the way to port D3, which is connected to digital pin 7, sorry. Now we know that 0 and 1 are mostly used for serial communication. So you've got transif and receive, and then the interrupts, which is something I really want to talk to you about, or I intended to talk to you about today, or if we are to have a next class, that's what we're going to talk about. But I will provide a video for you to catch up on, because I'm expecting you to use interrupts in your assignments wherever possible. Okay, so we decided to use PD5. Now, if you are like Abimbola and want to get creative and want to change from PD5 to a different pin, make sure that the corresponding pin is set the right way or is set accordingly. So we made use of pin 5 and pin 2. If I remember correctly, I think pin 2 was the digital switch or push button, and pin 5 was the LED. It doesn't matter if you change it. If you change from pin 5 to pin 4, you need to make sure that you set the correct pin on. Now, to make life easy for ourselves and to make things quicker, I'm just assuming that some of us haven't created the circuit yet. So if you haven't created the circuit at all, basically you can go in here and copy the circuit from there, which is what I simply just uploaded to you a few seconds ago. So you should be able to have access to this circuit that I have. It is taking its time as usual. All right. If you don't have access to the circuit, please download it from here. It's available to you, or now you can simulate it on there. I'm trying to get it open as well. I do not want to restart my computer as it will interfere with the class. Okay. So quick recap. My Tinker card is still uploading on the other one, but we go through here. So to quick recap, I will just comment this out, and we have done this circuit before, so none of us have a problem with getting the push button to work. But here's the emphasis. I'll go to this code. Oh dear. Right. Too much. I should be perfect, right? So quick emphasis here. What do we have? We have the push button connected to pin 2, and then the LED pin connected to pin 5. So I am going to open. Abimbola, are you happy for me to share your Tinkercad as well with the class? Okay, no response. I'm just going to assume that she didn't hear me, or she's not happy for me to share it with the class. Okay, so we have the push button as pin 2, and then the LED pin as pin 5. And on the push button, we really want to use it as an input pull up. Input pull up, we saw earlier that on the 18MegaThread2AP, we get access to we are able to configure a digital I/O as a pull up, or just connect to a high voltage source. And then when it gets to the coding side, so basically we are passing the value of the push button to a variable, and then we check the state of that variable. If the variable is low because we are already on pull up, we simply want to already on pull up, which means originally the state of the switch is 5 volts. So if we press it it just creates a connection from pin 2 through the switch to the ground. So basically that's the connection it creates, so it becomes a 0 volts. So if the switch is pressed, that'll be a 0 volts, and you want to turn the LED on. If the switch is depressed, you want to turn the LED off. Now let's say if you change this to LED to, let's say, pin 4. If you change to pin 4, I don't want that. Okay, so on the code inside, now I have to get rid of that if you allow me. Okay, so back up, undo whatever I did earlier on, so we have access to it, and I don't want to save this. It's going to ask me to save. Okay, get rid of that. Right, so basically if you change the LED pin to, let's say, pin 4, you have to note that you are using pin 4 here, so you need to make the right changes in the code, and I got this question earlier on, so make sure you make the right changes in the code. All right, so if we simulate this, if it will run for us, basically press, the LED goes on and it goes off, so that we are comfortable with and we are okay with. Last week we walked through this code step by step and we programmed it ourselves. This week I'm just going to jump right in because the comments are there. The bits that we got rid of are commented there. Is there any question for me so far? Good. That means you can hear me. Is there any question for me? Okay, right. Good. At this stage, that's fine. Okay, we are sort of comfortable-ish. Right. Now we get rid of this. Try to pull out the reference. We can make use of the Arduino reference, and I said this is available to you, and you've got bitwise shifting on there. So don't confuse that with the logic operations. Logic operations are usually double versions of this. So you can either shift right or shift left. Now, if you, let's say, shift to the right, you are performing multiplication, okay? If you shift to the left, you are performing division. I will explain to you what I mean by that. Please, I just want to explain the bitwise shifting because that's where we have issues with, right? Please, if you have, if you don't understand, just jump in as we go on. So basically, if I have binary numbers, 0, 1, 0, 1, then I've got 0, 0, 1, 1, each delaying by powers of 2, right? So if I was to go here, it's going to be 0, 0, then it's going to repeat 4 times and the same powers of 2. So if I have 1 bit, I have only the maximum I can represent is what? 1, which is actually 2 to the power 0. That what you get is 1. Now, if I have 2 bits here, so if I move this one to the next one, I'm basically performing a multiplication times 2, right? So if I move it to the, well, if I move it to the left again, it becomes, so here originally it was 1, then it became times 2, it became 2, now it became 4. The same, if I keep going, it will become 8, and so on and so forth. So the more you, each time you shift to this side, you are performing a multiplication. And if you think about it at the low level, this is one way of implementing a multiplier in the arithmetic and logic unit if you want. And obviously it's a bit more complicated than this, but quite similar. The same way, if we shift to the right, we have 1, 0, 0. Now if we get rid of, we shift to the right, we get rid of 1, 0, it becomes division, because now we had 4, now we are with 2, and then if I shift it again to the right, it becomes a 1, it becomes division, so it's division by 2. That being said, we're quite clear on that, and we are looking at the shifting to the right. So the same thing, you notice that on here, if 2 to the power 0, those whose hands are up, I'll lower it for you, so at least I can carry on with the class. So if you are doing a shift to the left, which is multiplication, on here, how many bits do you want to shift it? Basically counting from 0 to the power 0 is what? A 1. That is why we have the results being a 1 on there. So if I shift it again, then it just basically just becomes 2, which is 1 0 on there. And if I shift it again, then it becomes, let's say how many bits that we want, it becomes 4. So what that means is that if we've got 8-bit, or let's say sequence of ones and zeros, so if you got this and the width being 8, so you've got 7 to 0 as your width, or in terms of bits that you have. So that being 0, 1, 2, 3, 4, 5, 6. So you have 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So when we say we shift a 1, sorry, I didn't share the other screen, but we got it. I'll go back to share the Arduino reference with you. It's easier to write on here. So once we shift a 1 by what? The first bit, that 1 is put on here. So the value that we have is simply a 1. Now, if we shift that same 1 to by 1 bit, so move this away or write it at the bottom. Get power into the computer. So let's say if we shift that 1 by 1 bit, is going to be the bit that we specified on there. So this is bit 0, this is bit 1. So let's say if we want it to be in bit 5, so we simply can access bit 5 straight away by doing this, which means we start counting from 0, 1, 2, 3, 4, 5. So this kind of a pretty straightforward way of assessing individual bits of a given data. Is that understandable so far? If yes, please, I prefer you say yes, so know that you are acknowledging that yeah, you are happy with what I've explained so far. Okay, perfect. Everybody sort of understand what we've gone through so far. Okay. Now, the same thing that we just explained, that is the significance of this particular table. So basically it gives you quick access to which panes that you are. Jamshed, it's quite good that you're showing your face, really. At least I can identify with it. I wish everybody did the same. But anyway, back to the point. So this is the significance of that table there, and it's available to you. It's all online. You have access to it, and this is even not on the now side itself. I can put a link to it if you want. Okay, so that being said, we need to come back to the port somehow. Now, that is where it gets interesting. I can go back to the whiteboard to show you some stuff. If we prefer, we are interested in 2 pins, and the pins we are interested in is pin 2 and pin 5. Okay, pin 2 is connected. Pin 2 is connected to PD2. Pin 5 is connected to PD5. Now, PD2 is the switch, and PD5 is the LED. That's what we understand so far. So back to the whiteboard. Now, you know we have 3 registers. Can someone say a name of any register that they remember? In terms of the module I/O. Okay, silence means we are either still typing or nobody want to take the lead. Right, so we have a line. Now we know this line, yep, these ports or these lines can be used either as an input or output, right? We know it can be used as it's very simplified version of it. Of course, there's circuitry going on, which is controlled by ones and zeros. So some way, somehow, if we are designing this, we need to find a way to tell the direction of the register. So the data direction register, which is DDR. Now we can have data direction register X, where X represents the port, and we have said earlier that with the ATmega32AP, we've got 3 ports or 3 IOs that we have access to. We have access to D. Well done, McDonald. Listing all of them out. We've got access to D, we've got access to C, and we've got access to B. Now we all know that D and B share the digital IOs, so they share the digital IOs, while C mostly take the analog pins. So you have A0 to A5. So the same circuits that we are using, if you were doing analog read, it would be port C that you'll be accessing. So this is quite important. If you are doing your assignment, please remember. Okay. So now we know that port D0 and 1 are used for the transmit and receive, and then 2 and 3 goes to the interrupt pins. So if I ask you to make use of interrupt, remember you are aiming for 2 and 3. Now, at the same time, in our circuit, we made use of pin 2, and then we made use of pin 5. Anyway, so back on here, it means we are interested in data direction register D. Now, in here, we get to decide whether a line is or a particular pin is an input or an output. Now, an easy way to remember, I would say I expect I to be the input because I looks like 1 looks like an I, and I expect 0 to be the output. That's my expectation. Don't confuse yourself at this stage, right? But then I remember, as far as AVL architecture is concerned, is the inverse rather. So if I is I expect 1 to be an input, 1 is actually the output. So here is 1 if this is out. So 1 is the output, and then 0, which I expect to be the output. The inverse of that is input. So basically 0 is an input. Now we remember that data direction register is a port, so it means this is 8-bit wide. Which means as you look at the ATmega chip, as we saw earlier, you have these pins, and these pins can be 0 to 7, for example, right? And then we have picked pin 2, which is actually the 3rd pin, and we have assigned this. I've got a question. Okay, so so basically asking me to go through this, and then all about how ones and zeros, yep, codings are done, and that is the purpose of a low level or systems designer. We've done the high level stuff, and you are doing high level stuff with Suraj and James anyway. So this class, we make things possible. We made the hardware possible, right? So hardware is ones and zeros. Somebody have to design the stuff, and understanding of how to manipulate register is important, because once we create it, then the software engineers find life easier. And as I said, if you understand how these registry work, and even things like superscalar and other stuff, you can optimize your codes better, or like knowing things like not using jumps unnecessary. Or last week we looked into the memory, so you know how to actually not to waste space or not to waste memory. Anyway, back to the class. Now let's say we are interested in pin 2, so this pin is something we want access to, and also we want to 2, 3, 4, 5. Definitely that's not 7. Let's say 6, 7. So we put 7 on there, and then this is our pin That's our pin 5. I may got to get a count wrong or something. So we are also interested in this pin. For this particular circuit, we don't really care about the rest yet for this particular circuit. Okay. So these are the two that we are interested in, and we said pin 2 is a push button switch. So basically you have well, wrong signal, but you have a push button switch on there, or you've got a switch that you're split to close. Now this switch is an input, so because pin 2 is an input, we want to set pin 2 to a 0 from the beginning. So you can write something like this: pin 2 as an input, and in order to configure it as an input in the data direction register, you expect pin 2 to be 0. Now pin 5 is an output because it's an LED, so it's light emitting diode. That's pin 5. So we will send a 1 to it. So we want pin 5 to be somewhere here. So in the data direction register D, DDRD, we really want to have a binary where it doesn't matter, as long as pin 5 and pin 2 are concerned, we will put, let's say, a 0 on pin 2 and a 1 on pin 5. And by default, the rest are all 0 anyway, because by default, they are set as an input. And we had a look on the data sheet that way to see how they are. So this is the configuration we want to have initially, like our pin mode, right? So the pin mode, the mode of what we are doing, we're simply setting this as an output, that as an input. Okay, that's all we are interested in at this stage. Now we are not done yet, because what we want is to connect the push button through a resistor to the 5-volt source. Okay, that's the input pull-up. That's what we want, right? We want input pull-up. Now, input pull-up simply means that we have to some way, somehow force this to become 5 volts. So first line we're done. We've just set it as an input. Now we want to force it to become 5 volts. Now, what we understand is that we have our data direction register, and thanks to everybody who answered earlier, we also have our port, right? So somebody said thanks for the additional support. Thank you for your acknowledgement. I appreciate that. So basically, if we look at, let's say, the registers, now data direction register just sets the direction. And then we have the port. So the port is capital actually, so just make this caps. So port X, and we are interested in port D now because that's the only one we are connected to. Remember, if we were making use of the analog, this will be C, and that will be C as well. So we've set the direction. If it is an output, we know if we have an output and we send a 5 to an output, it means that pin just gets 5 volts assigned to it, which is a 1 or a high, right? If it is an output and we send a 0 to it, that pin just gets 0 volts, which is a low signal that we are dealing with. Okay, so when it is an output, we don't have much of a problem. So it means, especially for pin 5 is configured as an output. So if we send a 1 to port on pin 5, we expect the LED to come on. If we send a 0, we expect the LED to go on. That is pin 5, port D pin 5. Okay, but how about if it is an input? If it is an input and we send a 0 to the port, we don't expect anything to happen because we are simply connecting to ground. If we send a 1 to it, what we are actually doing is connecting that signal to the 5-volt source. So what we want to do first step is to do the pull-up. So it means we go into port D. So port, let me just use PD for some reason. Mouse is getting wrong. So if we go into port D, and what are we interested in? We want to set the input to pull up. Now the input is what? The input is pin 2, the switch, right? That is where the input is. That's our switch. So we set that pin to 1. Now, in order not to confuse ourselves, let me put 5 volts here so we don't confuse the pin. Now, it doesn't hurt to set the LED pin off. So the port option, we are actually doing a digital write, but this digital write is actually combining both the pin mode and the digital write, because before in pin mode we can just do pin mode input pull up. So what we are actually achieving, we are using a digital write to achieve a pin mode here, but at the same time we can do two things at the same time, which is the benefit of using the ones and zeros. We get to combine stuff, right? So if we go to that binary, we can keep the rest 0. So we have achieved two things with one line, and that's all we want. Just these two things. Basically, switch the LED off and then turn the 5 volts on. That good so far? If you have a question, please type. Otherwise, simply say no, for me to know you have no question and you are satisfied so far. Okay, so please pause with the testing. Somebody wrote something. I now understand why be that pin mode. Okay, good. So no, then okay, no questions and other things. So we are still on the whiteboard. Now there is one more register that we are interested in, which is the pin register. And the question is, why do we even need the pin? And remember, the X just corresponds to the port that you are using. We are using pin D here because that's what we are accessing. So far, with the data direction register, we've been able to set the direction. With the port, we've been able to kind of initiate some form of pin mode or even digital write on there. So with the port, we're able to write to a pin, or we're able to set an input as a pull up or just pull an input down. Okay, now we need to find a way to read the state of that pin. So let's say now we want to find out what is the state of B5. So if we look at pin D5 and we are able to assign it to, let's say, a binary number, right? Just look at it alone. At this point, D5 should return 0 because we've set D5 to 0. D2 should return a 1. So pin simply tells you the status of that pin. So it is a way of doing a digital read or an analog read. Can I clear the screen? Are we happy with me clearing the screen? I would like to select some stuff, but if it doesn't allow me, then great. Yeah, I'll just clear the screen. Thank you very much, guys. Okay, so what we have so far, if I remember correctly, we've got the binary number, and then we had pin 5, and then we had pin 2, and then initially we set pin 2 as an input. So 0, remember, input, output, the inverse of it. We set pin 2 as an input, and then we set pin 5 as an output. And we have these binaries in between. Then in order to do the pull up, okay, to do the pull up, we achieve two things. We switch the LED off, and at the same time, we set the input pull up by connecting the port. So this is port and this is data direction register. We set that particular pin to 1 because it's an input. If it's an input and you send a 1 to it, you are just connecting to the 5 volt source. All right, still thinking low level thinking. We've done hardware solutions. We are happy with that, right? Now we want to do a bit of some fancy play. Why we needed those binary shifts before we jump into things. So now it's hopefully fresh in your mind, and we can still get back to it. All right, instead of just memorizing it. So now what we want to do is to read the state of a switch. Okay. We've got our 18 mega 32AP, and then we have a pin, 2 pins we are interested in, all on port D. Now we know that pin returns the status of that particular pin we are interested in. So we know a way that we can actually find the status of this line, or let's say this connector. Okay. But we really have no way of telling. We don't know whether it's a 1 or a 0 or 1, right? 1 or 0 or 0 or 1. We really don't know yet. So we have to find a way of determining the state of this line. So one way of determining that state is actually to use a reference. So this is our reference signal. Okay, that's our reference signal, and then this is our actual switch pin. If we know the reference of this signal, let's say, which can either also be either a 1 or 0, we can use that reference signal to compare the state of this switch, and then that will set the output to what we are interested in. So this is our expected output, which is a variable. Please, there's not output pin, so let's call it variable. Cancel this. Hold on to that thought and just hold on to it for a second. So we will come back to this reference stuff. Now we know that each time we do a shift to the left, we are performing a multiply by what? 2. And we can simply pick the very bit we are interested in by simply using the power. So if you are interested in bit 5, we can simply jump straight to 5. Or with regards to what we wanted to do today, you can actually use pin D5, but there's no fun in that. It's just a bit. Anyway, we'll get back to that some other point. Right. So if you want to shift it to 1, you can just simply use a 1 there. So you just simply use the bit that you are interested in. So here we are interested in bits 2 and bit 5. First of all, we want to read the switch, which is our bit 2. When we want to write to the LED is bit 5. Okay, so we know that we are interested in bit 2. But bit 2 has also been called button switch or button pin in your code, or the code I've given you. Because earlier on we defined button pin as what? 2. Okay, so that's an information that we can make use of. So simply, if we shift by 1 to the left 2 times, well, not 2 times, to pin position 2, what that simply means, as we look at the reference earlier, is the 1 will be moved. This is when we did 1, and then it will be moved again, and then we'll put a 0 there, and then we'll put it there. So here we jump straight to bit position 2, which means we get access to this particular pin, right? Okay, so if we take the pin D, which at the moment gives us access to all these current states that we have. So at the moment we have pin D being equal to 0, 0, 0, then 1, 0, 0. And we say we have our pin D. What we want to find out is we want to make use of the button pin. So we want to access the button pin. So we have pin D, and we want to pin D dash something can help us make use of the button pin in pin D. Okay, that's all we want. That's all we want. We want to find a way to get access to the button pin. Okay, now what we know is that we have an input. We don't know how to access whether it's a 1 or 0, and then we have a reference. Now we have control over this reference. So the reference, we can set the reference, the bit on that reference to what? 1. So in order to set bit 2 of that reference signal to 1, that's in order to have 1 0 0, what we have done is actually use this function, or this line, which is move the button, move 1 or bitwise shift 1 to bit position 2. That is all we've done at this point. So this is our reference signal. So we know definitely that we are setting bit 2 to a 1. Now what we want to do is a read, right? Are we all okay up to this point? Please say yes. Let me know you are with me. All right, we are okay. We are okay up to this point. That's good. That's good. We stay on there for now. We are okay up to this point. That's perfect. So we have this reference signal that we know, because at this point we know that the bit value that we have 00001, right? We know the bit 1 is set. Okay, so if I have my signal, which I know that particular bit is a 1, and then I have the unknown signal, which I know can either be a 1 or 0. And I'm saying, what do I want to do? What I want to do is, if this unknown signal is a 0, I want my final output, my Z. I want my Z to be a 0, because that's all I'm trying to do. I'm just trying to use this to force the value of Z to be equal to the actual signal I'm interested in. So basically, I want to replicate this signal on Z by using a 1 to force that bit. So I say, if I have a 1 and the output is the signal is a 0, I expect it to be a 0. If I have a 1 and the signal is a 1, I expect it to be a 1. And I think about it. So if I put an OR gate here, this won't work, because OR gate, I will get a 1 on the output. How about if I put an AND gate? If I put an AND gate, then it means both did not happen, only one happened, so the output is a 0, which is good. It's the same as I expected. And if I put an AND gate there, the output is a 1. So as expected, simply, if I pick my signal, which I want to read, pin D, currently the switch, because remember, this is the whole of pin D, right? Or pin, yeah, the whole of that port. So the whole of pin, the status on port D. But let's say if I pick pin D, and then I do an AND on that particular, I do an AND with a 1 on that particular switch I am interested, on that particular pin I'm interested in this case pin 2, which is the same as button pin. So what I'm saying is, I'm picking pin D, which is here, which is this now, and I'm saying, okay, let's get rid of this. I'm saying, okay, I have a 1. At the moment, I set all this to 0 by using the bitwise shifting, and I have a 1 here. Then I perform an AND with it. My style of AND writing AND changes all the time. I perform an AND with it, so I get the actual state of that pin. Because if it is a 0, I get a 0. If it is a 1, I get a 1. Right. So first of all, I do perform this operation, and then what I want to do is to save it into a switch, which is a variable. So let's say an integer variable. Now remember, integer is 16-bit wide, and at the moment we have, let's say, even if we have 8 bits, even if we called it bool or whatever, at the moment the value in this particular, okay, whiteboard is difficult to follow. Is anybody else having issues with the whiteboard? If you are having issues with the whiteboard, let me know. I've cleaned it now to make things okay. So a few clarifications where I will actually things I will clarify. Remember, we use port we use port to write to that particular port. If it is write either 5 volts or a 0 volt to that particular pin, right? Now, if you write it to the whole port, it's going all the way to the whole 8-bit. But you can actually use a binary of 1010 to access individual pins. Is that clear, Bimbola? If that's a yes, you say yes. Okay. Now, basically, we use the pin to tell the state of the whole port. So if I go to pin D, remember it's still 8-bit, but I'm using binary, so I can read the state on each individual bit where we use 1010. We can use binary to detect the state, right? So we can use binary to detect the state. And then what we are saying is if we put an AND, whichever pin we are interested in, we will set that pin to a 1. So let's say if at the moment I want to read this pin alone, which is maybe a D7, right? I will just shift a 1 7 times to that position. So it will go all the way to that position. And I can be able to read what is on there. So I can still get, if it's a 1, I get a 1. If it is a 0, I'll get a 0. And then all these, if I add this with 0, all these will become 0, 0 anyway. Okay, so that is clear. So it's pin D refers to the whole port, but you can actually pick some particular bits you are interested in this way. The person who complained about the whiteboard, I keep deleting the whiteboard to make things simple so we can move to the actual coding bit. And that's why I copied the code for you. You can have access to the code and walk along with me. So last week we used the board to explain it. This week I'm using slightly different approach for the rest of us to catch up with it as well. Okay, is there any other question before I jump too deep into it? Okay, so no question. So far what we have done is we've picked pin D, we've done our AND, and we did an AND with what we wanted to do, the bottom pin. So basically we chose, we can choose the binary or simply just make it simple. Last week I think I started off with the binary. So we want to shift it 1 to the position of the bottom pin. Okay, so try not to jump back and forth too much, guys. Data direction register. Okay, so we'll hold on to this. I'll write this at the bottom. So data direction register, or DDR, sets the direction of the pin. So it sets it as an input or output. And remember, if you want it to be an input, you put 0 in the corresponding pin. If you want it to be an output, you put 1 in the corresponding pin. Now, the port register. So data is just a hardware. That's all it does. DDR simply sets the direction, right? And the port register is where you can actually set. So we've set the direction. If let's say this is connected to an LED and we want to say put a 5 volt to the LED. So we've got LED, we want to put a 5 volt to it. We, after making sure the corresponding pin, in this particular case 5 is 0, in the port register, pin 5 of that particular port, let's say port D, we will send a 1 to it. So as soon as we send a 1 and it is a 0, it will be connected, and 5 volts will be connected to it. If we want to switch it off, we will send a 0 in the port. So we use the port to set the value of that particular pin. DDR set the direction. Arathi, I hope that answers your question. Now, if it is an input, you have an input. If you send a 0 to an input, basically you're just connecting it to the ground, so that input is grounded. If you send a 1 to that particular input, so which is in this case pin 2, which is an input, so we have pin 2 there. If we send a 1 to it, you are simply connecting it to the pull-up resistor, so you are just using pull-up, and by default the state will be a 5 unless you press it. Arathi, I hope that answers the question. Yeah, and hopefully anybody else who had doubt or did not get what we were explaining. Right, so I have to clean the whiteboard somehow to make things simple for us to follow. So basically what we have is pin D. I'll just use P for it as well. So the whole of pin D, which is 8-bit. Guys, please do not write on the screen because you slow the whole class down by doing so. Right, so we've got pin D, and pin D is 8-bit wide. So we've got pin D 8-bit wide, and we are doing an AND with the button pin. And how do we know we've got the right pin? We do bitwise shifting to that particular position. So this jumps to the button pin. Okay. Now, what we understand so far is all we have created at this point is whatever value that this is actually equal to everything else being 0 and the button pin, which is pin 2, being set to 1. Everything else being 0, right? And the button pin being set to 1. Now, if we assign this to switch, if we assign this to, let's say, an integer called switch, what have we done? The value here is actually what? If you convert this to binary, what you have is the ones being 0, the 2's being 0, and the 4's being 1, and 4 times 1 is 4. So currently, yep, as most people have clearly pointed out, currently the value of this switch is 4. But remember, in our logic, what we want to do is test if the switch is equal to low, which in other sense, or in other words, we are saying if the switch is equal to 0, do something else. If the switch is equal to high, do something, which is if the switch is equal to 1. So we can't necessarily have that kind of flexibility with a value of 4, right? So what we want to do is to take that binary number, because we have access to the binary number here. So we can take that resulting binary number and then shift it back by the same number of bits that we shifted in, because what we want at this point is to ensure that the state, we are getting the right state of something, whether it's a 0 or 1 with an AND. So we shift it back by the position that we shifted with. So basically we're doing a shift back or division by 2, which is bit 2, or we are doing a shift back by the button pin. What does that create? We're going to shift it by 2. So at this point, it turns out to be B. Whatever we have is already 0. And then the 1 gets shifted to bit position 1. Now, if we convert this to decimal, we have a 1. If the result there was a 0 and we shift it back and the 0 gets there, if we convert it to decimal, we have a 0. So that actually validates what we want to have, and hence make sure that the value of switch, it will always be either a 0 or 1. That's all we're doing at this point. Now, that being said, if I clear the screen, if we go back and I share my Tinker card with you. So let's go back to the screen. All right, so first of all, we understood up to this point, and up to this point, we've achieved two things, which was to switch off the LED and also connect this to the pull-up resistor. So if actually we want to, you can comment it well, but this is the previous code. You are not achieving exactly the same thing with it. I just left it there to make it simple for you to follow. And at this point, we have switched on, we have read the state of bit position 2, and then we know whether it's a 1 or it's a 0, but the value is turning to be either 4 or 0. So since it's 4, we don't really want to read 4, we want to read just a 1 or 0. We shift it back to the position, and up to this point, all we've done is to read the state of the switch. So we either have a 1 or 0 here to perform this logic, and that takes us now to these particular two lines of code. Is there any question at this point? If it's all clear, please say yes. If you have a question, then you ask the question. Okay, so for the few who are following, I'm glad that at least this makes sense to you. Arathi asked another question. So switch equals low compares the last digit. So Arathi, to answer your question, switch is an integer, right? We've declared switch as an integer. And Arathi, I'm working with you now. So if we have a binary number 100, what is the value in terms of decimal equivalent? The decimal equivalent is 4. Now remember, we simply, if we say if switch is equal to low, low is actually a 0, okay? And then high is what? A 1. Is that clear, Arathi? Yeah. So at this point, it is 4. If we can't really tell whether this is a 1 or 0 because the lowest bit will always be a 0. Does that make sense? In binary, the lowest bit will always be a 0. So all we want is we are interested in a 1 or 0 on a particular bit. So since this is equal to 4, we don't want to represent it in 4. We can shift that bit back down to the lowest bit. So if we have, here's another question, if we have a binary number and the least significant bit is a 1, what is the value in decimal? Yeah, the value is a 1. So if the least significant bit is a 0, what is the value in decimal? A 0. Good. So when we say if switch is equal to this, at the moment we have forced, because all the rest is 0. So at the moment we force the value of switch to be equal to 1 if the previous calculation was 4, or to be equal to 0 if the previous calculation was a 0. So we can actually have a valid state for low or high. Does that answer your question, Arathi? Good. All right. Now, what we have is just the similar idea. We have a signal. We have a signal which can be a 1 or 0. We can't really tell what it is, but we can make use of a reference which we know, reference bit which we know for sure is a 1 to read the state of this signal. Okay, it's all about reading. Now, before we use an AND gate to basically force the state of that particular pin. And what all we want to do is at this point we have our signal 1, and then let's say we want to force the value of Z. Okay, we want to force the value of Z because we want to say digital write something to high. We want to say force Z to be high, force our LED to be high. That's our interest now. We want to force Z to be 1. Then we have 0, 1 for the current state of the pin that we have. And then we know our reference. So using shift, we can access any pin at all that we want by using the variable position, right? Now we say if the state is a 0, we want it to force it to be a 1. So 0 will become a 1. If the state is a 1, we want to force it to be a 1 as well. So we just use our 1 dash something should be able to combine with this somehow to create that. Then we are thinking circuitry, right? We're now working at the lowest level of the hierarchy that we looked at in the previous weeks. So we say, what kind of circuit or what kind of gate or logical gate can we combine with these two, that if I have a 0, it becomes a 1, and if I have a 1, it becomes a 1. So I can say this is my X, this is my Y. X changes from 0, 1 to 0, 1. And then Y changes from 0, 0, 1, 1. Now we say there's no way that this is going to be a 0, but we don't care anyway. So let's say we don't care, but suddenly we care. It should be a 1, and this should be a 1. So simply it becomes an OR gate. Well spotted, Arathi or whoever. So it becomes, yeah, it was Arathi. So it becomes an OR gate. So simply I can pick my signal and then use an OR with my known bit, right? The bit that I force to 1, and then force that particular pin to be a 1, which is the LED pin. And we know the LED pin is bit 5. So if we take our bit, and then we have bit 5, and we want to force bit 5 to a 1. So basically we say bit 5 now can be either a 0 or 1. Current state, we don't really care. But if we say shift it by the LED pin, which previously we have defined to be 5. So it's going to jump all the bits to bit position and put a 1 there. Guys, please do not write on the screen. It will slow the class down, and I'm only doing this because you have requested for me to go through it. Thank you for your cooperation. Right, so we shift it to that. Yes, you can use decimal equivalent if you want, but why bother when you can play with ones and zeros, and it's really cool. Anyway, so you can jump, we jump this all the way to the 5th position, and then we do an OR. So our LED, if we assign this to the LED pin, which is pin 5 on what? Port D. So we go to port D pin 5. Now we'll talk about this in a minute. This is actually a valid variable name, and you can use it anywhere. So because it's an OR, if the LED pin is off, it will come on. If it is on, it will still stay on anyway, because our reference, that is what we are doing. Okay, now because this is port D, if we want to assign the whole thing to port D, if let's say we pick, so we've got the bit, and then we pick 5, and then we do an OR with our reference pin. So we have an OR, we pick another bit. Let's call this the reference bit, right? So we do an OR with 0, 0, and then we have a 1 on the pin we are interested in, the rest 0. And we write to the whole port. If we write to the whole of port D, if this is a 1, because we did an OR, it's still going to end up a 1. We don't care about that. We don't care about these. We don't care about that, because we are doing an OR. It wouldn't change it. But the bits that we are interested in will be forced to a 1. That is why we do basically just an OR on there. So the alternative on here so this actually switches on the LED. We get that. We are happy with that. Everybody's happy. Nobody has raised concerns. Switches on the LED. Now we have to find a way to switch off the LED. So to switch off, let's say we have our signal. We've got a bit 5. We want to find a way to turn this off by using our pin. Now we know the way to access individual pin is just using this one, and then you shift it to the pin, that position that you want, in this case 5, or you use the variable name, which is what we have been using, the variable name. Okay, so we get access to this particular pin now. Now we say, what can we do with this one to ensure that actually the output is a 0 if it is a 1, and the output is a 1 if this value is a 0. So let's say we find out. Let's try some few things. Yep, well spotted, David. So basically, let's say if this is a 1 or that is a 0. So let's take our B, pin 5, put it here, and then we've got these two states. And then let's say we use our 1 there, which is the reference that we have. So this is the reference, this is the actual value, call it X. So if it is, we put an AND, for example, an AND, we expect this to be what, a 1 and a 0, should we expect the output to be a 1? Kind of work for us a little bit. And then if this is a 1, we expect it to be a 1, and a 1, we expect it to be what? A 1. Nope, a 1 and a 0, we expect it to be a 0. I do apologize. Hence, forcing us to know the actual state of X as we have done before. So through this, we get the actual state of X at this point. Then we say, okay, we managed to read the actual state of X. We simply have to not it or just invert it. So we use that, gain the value of the state of X, and then we invert it. So if we, let's say, cross out this stage, we notice that we move from 0, end up with a 1, and when we move from a 1, we end up with a 0. So previously, just as we read the state of X or the signal with an AND, now we read the state of that signal, and then we simply use an AND NOT gate to invert it. So AND is a digital read, digital write is an OR, and then digital write for a toggle is you do an AND. So you do an AND and then you invert it. So basically you could pretty much familiarize yourself with these, but I don't recommend that you memorize things because I prefer you understand things. So if we go back to our screen, oh dear, I see it flickering at the top. I'm not sure whether you see exactly the same thing, but it was doing something for me. So if we come back here at this point, we find the right bit, and then we do an OR to read that particular bit, right? Or to write to that particular bit. So basically we force in that bit to be a 1 or 0. And then we use the AND to read the state of that particular port or that particular pin, and then we assign it to, we toggle it. And obviously to do a write, we need a port, and then we make use of a port. So that's basically like a step-by-step approach to explaining how we have manipulated the registry or work with the registry so far. I'm going to stop the recording here. If you have a question, please ask. It's